But okay, so the agenda for this one, we've recently in the Unit 3-4 classes finished up a bit of polynomial stuff. Now it's time for the Unit 1 and 2 guys to have a crack at the polynomial stuff as well. And so we're basically going to be running through those again. We'll go through a bit of an introduction to polynomials and then work our way up to polynomial division. So let's have a look. What is a polynomial? We're looking at the screen share for this one. So a polynomial is basically any sequence of power terms, right, where you have all these coefficients of x to the power of something. Like for instance, x to the power of 3, that would be like an x to the power of 1, x to the power of 0. You have a sequence of x to the power of something. Just a bit of terminology, the degree of a polynomial is equivalent to the highest power of that polynomial. So whatever n is the most leading term here, like in this case here, this would be considered a third degree polynomial because it is x to the power of 3. A bit about how we solve polynomials. It is going to be very similar to how you solve quadratics, if you're already familiar with that, where a lot of the time what you're trying to do is factorize it, get it into a sequence of terms that are all multiplied together, and then use the null factor law to solve from there, which is to say that you look at each separate term individually and equate it to 0, and then solve each of those terms individually. The reason why is because anytime you have something multiplied by something else and the result is 0, either one of those terms would have had to be 0. For instance, if you have 8, to get it to 0, you would have to multiply that by 0. Or you could do 8 times 0, 0 times 8. In any order that you multiply something by 0, you always get 0. So that's essentially what we're doing with null factor law. We're saying this thing possibly could have been 0, in which case x would have been 1. Or this thing could have been 0, in which case x would have had to be -2, so on and so forth. You won't always have a sequence of linear terms. You might have a more complicated term, like a quadratic term. Again, you're just going term by term and then solving it the same way you would always solve that particular term. In the case of quadratics, you can do whatever you want here. You could do the factorizing, which I've got here. You could do completing the square, which is basically the same thing here. You could quadratic formula. You've got whatever method you want for that sort of thing. Not all terms are going to actually contribute solutions to the polynomial. Like for instance, if you have a quadratic that doesn't have any solutions, so discriminant being negative, when you go through your quadratic formula, you would get like a negative in the root. It just means that this contributes no solutions. So the only solution to this polynomial would be x equals -3 from this term over here. We're all clear enough about like discriminant and stuff from early quadratics. If at any point you guys have any questions, feel free to like hop off mute, send something in the chat. Either way, happy to double back. Okay. So one of the first things that polynomials introduces, and it's kind of in quadratics as well, the same principle sort of applies, is if you have two polynomials that are equal to each other, like we're told here, f and q are the same, they are equivalent, then what you can do to solve one is actually just sort of compare it to the other. So for instance, we're told 4x cubed plus 8 is the same as this string of letters and numbers. Because they are the same, what you can essentially do is go term by term in the polynomials and compare them to each other directly. So for instance, you start by looking at the x cubed terms. This one is 4x cubed, this one is ax cubed. For those to be the same, they would have to have an equal sign between them. Very quickly, the x cubes will cancel out, and you'll quickly see that 4 is equal to a, one coefficient down. Next up, there's an x squared term in here, and there's no x squared term in f of x. So for that reason, the only coefficient that makes sense for that is going to be 0. There is no x squared term in f, so there shouldn't be one in q. And then that's just it, right? They obviously both have plus 8 in there. There's nothing further to do. This is called equating coefficients and can be used to solve usually you'll get like a sort of show that question, which will be like, hey, here's the function in one state, here's the function in another state, show that A, B, C are equal to these things. It's a fairly common question that'll show up in, well, yes, SACs and exams. It comes up quite a bit. Anything to clarify further about this approach? Cool. Let's step it up. So here's more so what's more likely to show up, which would be, hey, here's a quadratic, here's another quadratic that looks a little bit different. It's in its completed square form, or otherwise, turning point form. Now what do we do? Well, these things aren't as easily comparable, right? We can't just go, there's an x squared here and an x squared here. There's no x squared here that we can look at. So one of the things you could do is, first you could potentially expand this one out if you wanted to make it look like this. But in fact, I've shown both methods there. So for instance, if you wanted to elect to expand this, what you would do is, well, expand it, right? You've got x plus b squared. You expand that set of brackets out, distribute the a all the way through, and now these terms are a lot more comparable to each other. All right, you've got an x squared over here, an x squared over here, an x over here, an x over here. Constants, constants. You can now compare those. But the first method I've done is actually to just complete the square on this one. That also gets them into a more directly comparable way. So completing the square is just this equation here. Some people have like a method, a multi-step method to complete the square, where you would like halve this term, x plus half that term, and then subtract the square of it. I find people sort of get the steps back to front occasionally, so I'd rather just put an equation there in front of you so you can just sort of copy that down instead. But this is just fundamentally completing the square however you're already used to doing it. You complete the square on this thing. After simplification of all of that, you'll get the new form of f of x, which we can see is now a lot easier compared to h. Right, you've got something in front of a squared term with a plus or a minus at the end. I've got those here in the same line, and you can directly see, okay, well, a has got to be the 6, this negative 2 has got to be b, and this negative 10 has got to be c. Fair enough on how that's worked? The alternative would have been, you're kind of doing a bit of simultaneous. It's not really simultaneous. You've got the 6x squared, you've got the ax squared. Well, that's obviously a is going to be 6. Then you've got the 2abx and the minus 24x. But because you already know what a is, when you do that equation, you can sub in your a equals 6, and that's going to get you your b. Probably the most trickiest thing would be to realize that this ab squared plus c, all of that is a constant. Right, so when we're dealing with polynomials, any sort of function, actually, it'll be some function of some specific variable. In this case, it's the function f, and the variable is x. The reason why that's important is because that tells you whether the other letters in the equation should be considered as coefficients, just any old number, or if they should be considered as variables. So in this case, this is the function f of x, or h of x, same thing. Anything that's not x is just some number. And so because neither of these terms have an x in them, they are considered just some constant, which is why we're able to equate that to the 14. That's probably the weirdest part of this whole thing. Is it clear enough why those are related to each other? Okay. Cool. All right, well, that's a summary for that part. Before we move on to the second part, polynomial division, is there anything in there that needed a bit more clarification? Cool. All right, next up, polynomial division. Okay, so basically, the purpose of polynomial division is that it gives us a way to get our polynomials looking kind of like this, where instead of having a string of x squared, x cubed, whatever, x to the power terms, we want to try and get it into a state where we have a series of factors that we can actually solve. Because when it just looks like this, very hard to solve that just on its own. And so polynomial division is eventually working towards a way where we can get it into a factorized form. Although it won't be immediately obvious as to why, we'll work our way out there. So what is polynomial division? Simply put, you have some polynomial divided by another polynomial, and you want to simplify that result. Yes, a linear is in fact a polynomial. It would be considered a monic or degree 1 polynomial because there's an implied power of 1 on that x over there. Here's the steps, but that's a lot of text, so I think it'd be better off if we just sort of have a look and see what that actually looks like in a sequence. So here's our example. First things first, I've just sort of defined what each of the terms are. N for numerator, D for denominator. This is the numerator, this is the denominator. Set up the division, so the numerator goes inside this square root looking thing, and your denominator is going to go out the left-hand side of that. Very first step is to divide the highest order, this should probably say degree, whatever the biggest term is of the numerator by the biggest term of the denominator. So you do this one divided by this one, as I've sort of pictured out here. X cubed divided by x, fairly simple, x squared. All you're going to do is put whatever the result of that is on the top of your bracket thing. From there, once you have that, the next step is to take whatever that result is and multiply it through the entire denominator. So you take this thing, multiply it through by that entire denominator. I've shown you the sequence of what that would look like here. You'd have x squared times x for the x cubed. You would have x squared times 2 for the 2x squared. That result you're going to put underneath. Ideally, you would line them up. So the x cubes are underneath the x cubes, the x squareds are underneath the x squareds, so on and so forth, because that'll just make step 3 a little bit easier to do. By the way, you don't need to show this working on the side. That's just there so you know where this came from. If you're already at the stage where you can do this sort of stuff in your head, like just immediately write it down here, do this one, write it down here, that's perfectly fine as well. Your teachers aren't expecting you to write this sort of stuff on the side. Next up, once you have that, you're going to perform a subtraction. This is where having things in like vertically aligned can be kind of nice, because all you do is you perform the subtraction as you would like for any other subtraction when you would do it in like, when do you learn that? What, year 4 maybe? Wouldn't even know. So yeah, do each term by term. So my preference has always been to put brackets around this whole thing, which is simply to remind that this negative sign isn't just attached here, it's also attached here. So for instance, you do x cubed minus x cubed, which will always give you 0 here. And then you do x squared minus 2x squared. A lot of people will do the first one and then forget the second one here, and they'll think it's a plus. So that's the whole purpose around putting these brackets here. It's not required in your working out, but you do need to make sure you're putting this subtraction on that. The result should be negative x squared, not 3x squared. These are just zeros, and so essentially everything else is just going to drop down. Whenever you subtract 0, you're effectively doing nothing. Nothing to the result anyway. And that gives you a new result that we're going to basically repeat all those steps over and over again. So I guess before I do that, any of that need further clarification? Easy.
Can you do the top one again, like from before?
Top one again, like when we started?
Like the division one, yeah.
Yeah, cool.
Thank
So
you.
the division is you look at the biggest thing inside the bracket and the biggest thing outside. the bracket. So you take this x cubed and this x, and you're doing the inner divided by the outer. So that's this thing in blue, this one in red. You're always doing the inner divided by the outer for that first step. And you pop that up there. Then you take that result, multiply it through, and subtract whatever's left over. Cool?
Yeah, that makes sense.
Yeah, and we'll see me do it a couple more times as well when we go through this as well. Because once you do one iteration of it, you're now doing the exact same sequence, but now using this as your new baseline. So this is now the biggest term. You're looking here this time, biggest of the inner, and this won't ever change. Still the biggest of the outer. So you're now doing the negative x squared, the blue, divided by the outside, the red. That's going to get you to negative x, which you're just going to tack on to the end of whatever you had on the top. Then, once again, you grab whatever the result was. In this case, it was negative x, multiply it through the entire denominator, and put the result down here. So negative x multiplied by x plus 2, that's this bit here. Negative x times x, negative x squared, negative x times 2, negative 2x. Just sort of chucking it down here, again keeping these lined up. Last in the list is to do the subtraction. So negative x squared minus negative x squared. This is where things get doubly tricky. You've got to keep in mind how the sign analysis works. Double negative flips to a positive. Basically, every time you're doing this, you should always have a 0 at the front. If you are doing your own version of this and you don't get a 0 at the front, it means something's gone wrong, because this is just sort of the way it slowly decays down into nothing. So yep, you're going to get 0 here, and then this one would read negative 14x minus negative 2x. So again, making sure this negative applies. There's a whole bunch of negatives in here. It can be kind of complicated to keep track of what's cancelling out and what isn't, hence the use of the brackets. So yeah, this will double negative, cancel into a positive. So now you've got minus 14x plus 2x, bring it down to minus 12x. Once again, there's a 0 here, so this just drops down. And you can see as we're doing this, we're slowly decaying this cubic down to a quadratic, down to a linear. If we do it one more time, we'll see that it fully disappears. So last run through, this is now the biggest term. Divide by this one, grab that result, multiply it through, chuck it here, and without even thinking too hard, we can see these things are the same. Anytime you subtract something from itself, you're always going to get 0. That's what it looks like as a repeated sequence. You basically just keep going until you get some number at the very end, is probably the easiest way to explain it as of now. There's a few nuances to that, but that's the gist of it. Fair enough on what's going on, at least conceptually, there. Cool. So whatever the result is at the end may or may not be 0. Whatever the result is considered the remainder of the division, and whatever's up here is considered the quotient of the division. Or in other words, this is the part that could have been divided, that could be divided, and this is the part that could not be divided. So all that to say that if you were to perform this division, this could be fully simplified into this quadratic. In some other circumstances, you might get it to a stage where you do have some things left over by the end of it, in which case what you do is you still write out the part that is divisible, so the x plus 1 in this case, but whatever's left over, if that can't be further divided, which we'll look at why it can't, what you'll do is you'll write that bit, but have it divided by the denominator, basically indicating that this is the part of the polynomial that could not be divided. That's how remainder is expressed in the simplified form, which, let's be honest, doesn't really look very simplified. You typically don't ever really do this, or at least you're not asked to do this usually. But okay, so why is this second example even here? This is just to show that there's more than just linear you can divide by. You can divide by any polynomial, actually. The procedure is identical. This is only here to show you that some complications arise when you do have higher power terms. Like for instance, you start with your biggest terms and divide them, x cubed by x squared, you're now getting x at the front, right? So it's a much more drastic division. It's going all the way down to x rather than x squared. You're still going to take that result, multiply it through, but you realize when you do that, hang on a minute, I've got x cubes lined up, and now the x's aren't lined up. Not the end of the world. You can just put a 0 here and then put the plus x over here. That'd be probably the nicest way to go about it when you're learning it for the first time, just so you just sort of keep your line of thinking as best as possible. Still perform the subtraction. If you're not going to put in zeros, just keep in mind that this x squared doesn't have a term that it's subtracting, so it's going to go all the way down. There is no other x squared in here, but there is an x, so that one's going to get affected. And what you're essentially going to see is this is going to complete faster than this is going to get rid of. So for instance, if we get all the way down to here, after we've done it a few times, the next step of like the final loop would be you grab the biggest thing over here, divide the biggest thing over here. The problem is when you do that step, it doesn't fully simplify properly. You end up with a fraction. That is another, we'll call it a reason for stopping the procedure. So if when you do this division, you end up with a fraction with the variable still in it, that is no longer perfectly divisible, or no longer considered perfectly divisible in there, and so you're essentially just going to leave that as is. That's where you conclude, you go no further, and that brings us sort of to, well, what I was mentioning earlier with the whole, this is considered the remainder, so you chuck it there, and then whatever this is the denominator in that case. Fair enough? Anything in there that should be clarified further? Because this is definitely the hardest topic of polynomials, I would say, at least initially. It takes a few goes to get your head around even just the execution of it, even if you understand it sort of in concept. There's a lot of moving parts around. You know, you're doing a division, you're doing a multiplication, you're doing a bunch of subtractions. It's one of those things where you can make an error somewhere, and then that's something going to cascade down. So it's worth practicing this one quite a bit because it does show up Unit 1 and 2 a decent amount, at least in the books. In a SAC, you may or may not get it because, as you've seen, these take quite a while to go through. Yes, I was explaining it as I was going, but I mean, look, that's a fair bit of writing there. And so examiners are sort of put in a position where it's like, okay, well, I can put it in there, but I've got to give it a lot of marks because there's a certain timing element to it. We need to hit roughly 1.5 marks per minute. And if it's a long procedure, then they've got to give it more marks than it otherwise would be worth based on its complexity. Cool. All right, well, that's pretty much it for the lecture portion of that. We had a bit of polynomial introduction and then how we can work our way towards factorizing. In fact, let me sort of put a cap on that. So I kind of mentioned this whole polynomial division. Oh, hang on, I got a message. Is there any way you'd be able to do a quick recap? Polynomial division. Yeah. Wait, when was this sent? Have I done a recap of polynomial division since you've joined? Or do you want me to quickly run over it again? I'll take a thumbs up as yes, it's fine. Cool. Okay. Okay, so I mentioned that polynomial division was a way to get us into this factorized form. So far, it doesn't look like it's done that. What's going on? Well, real quick, you'll notice that this is an equation. You've got something divided by something equals something. All I've got to do is take this denominator, multiply it across to that side, and suddenly we have a quadratic times a linear is equal to that cubic. We now have what is effectively this. In fact, it might be exactly that. No, not exactly. But it'll basically look something like this. So as long as you know what your denominator is, or can otherwise find it, this is a method by which you can figure out what the other factor is, and then you move into basically null factor law stuff. That's where it's headed. But okay, so intro, we've got polynomial division stuff. We can I'll touch on at least a bit of the intro stuff, just to make sure we're still good with our equating coefficients. And then I think the remainder should probably be focused on polynomial division, unless people have any other preferences. Let's give one of these a shot then. We might do this live together, just to make sure we're all on the same page. So let me get this out. We're going to have a look at question 7, by the way. So if you already have a copy of this textbook, feel free to work off of that, so you don't have to click through like several tabs. I will bring up the handwritten notes section so we can all just sort of go through this live together. I'm just going to write out the question initially. It's going to be question 7a. So we've got, what's that? X cubed minus 7x squared plus 4x plus 12. And we're told that is equal to x plus 1 bracket x squared plus bx plus c. Cool. 7a tells us to simply expand, so it's actually walking us through it quite nicely. So essentially just trying to expand that right-hand side. How's that going to look? Who wants to take a stab at that?
Chris, did you say expand the right-hand side?
Yeah, that's right. So if we have a look at like 7a, it just says expand x plus 1, x squared plus bx plus c.
Okay. So first you'd want to multiply all the terms in the quadratic by x.
Yep,
So
that's going to
you
give
get
us,
x cubed plus bx squared plus cx. And then you want to multiply all of them by 1. So you get
yep,
plus x squared plus bx plus c.
perfect. Yeah,
And
just
then just
going
collect like
orderly in,
terms.
orderly in. Yeah, exactly, like terms. So x cubed, collecting like terms, what's that look like?
Just x cubed. And then
Yep, so just x cubed. There was no other x cubes in there.
you can get b plus 1 times x squared.
That's right, yeah. So you got the bx squared, you got the 1x squared, so b plus 1x squared. Nice.
Then you get b plus c times x and then
Yep,
plus c.
b plus c, x, and plus c. So yeah, we had a cx, a bx, so c and b, x. And then lastly, yeah, the c, that's the constant, no other constant there. Anything to further clarify on that for anyone? If not, have a read of part B, which we'll now be working on, which is to, now that we've achieved this, see if we can calculate what B and C now actually are, which I kind of got to zoom out a little bit for. Hopefully that's still readable. If not, you'll have it on your page as well, I suppose.
B is negative 8 and c is equal to 12.
Yep, those are both going to be correct there. So B, negative 8, C, 12. Yeah, where do those come from?
B plus 1 equal to negative 7 and c was pretty straightforward because just constant.
Yeah, that's right. So basically looking at both of these, this was an x squared term, this was an x squared term, therefore those things should be the same. B plus 1 equals -7, that simplifies to b equals -8. And well, yeah, you could look at this one if you wanted to as well, but this is a lot easier, right? You just got this c floating out there, you got a plus 12 floating out there, so it's going to be the same. Very good. Now this is where it's all heading. So part C, hence write that cubic as a product of three linear factors. Now that we have B and C solved, it'll allow us to do what C is telling us to do.
We want to do polynomial division.
Do we want to do polynomial division? We could. Is probably a better way to do it, but polynomial division does work. Yeah. How would you start it out if you had to do polynomial division?
Yeah. So x, like we're going to be dividing by x plus 1, and
Yeah.
we're going to be,
So what made you choose x plus 1?
it's a known. It's like a known thing. But actually, now that I look at it, we can just get a quadratic.
Yeah. Yeah, that's right. So just to quickly like follow up on like what that would look like. Yes, you could polynomial divide because kind of like what I was doing at the end of this, where I said, hey, you can knock this over to the right hand side. I'm talking to the screen share now, by the way, where you can look at this denominator and chuck it over to the right hand side. You can do the opposite. You can chuck this term as a division over here, and suddenly that's a polynomial division. You can actually do that. But yeah, you then found the better way to do it, which is to do what?
Sub in like b and c for the quadratic, and then just find factors for it.
Yeah, that's right. We know what b is, we know what c is, and well, plugging that in gets us a known quadratic. Factorizing a quadratic is a lot easier than doing a full polynomial division. So that would be, we've got the quadratic, oops, that's in red. We've got x squared plus b, so it's minus 8x, and then plus c, so 12. And then we're just factorizing that, however you like to factorize it. Whenever you got that, let me know.
It's minus 6, x minus 2, and x plus 1.
Yeah, okay, so did you say x minus 6?
Yeah.
Yeah, minus 6, x minus 2. And then, yeah, we had that x plus 1 from later. This would have just been some basic add together times together. -6, -2 make -8, and -6 times -2 get you to the positive 12. So yeah, that's a bit of quadratics revision there as well, and a bit on the equating coefficients. We could do a bit more of that if people want. There is another question 8 in there that's quite similar. Or we could go into the polynomial division stuff, which is harder. What would we rather do? Question 8 or move on to the division stuff? Cool. Let's do it. So again, because this one has a lot of steps to it, probably best we do at least the first one together. Now I say together, and I do mean together. I won't be saying what each of the steps are until I get at least a recommendation on how to start. Okay, so first up we would have to set up the division. I'll kind of just give that one because it's kind of hard to explain what setting it up looks like. So whatever the divisor is, which in this case is x minus 1, we're told to divide by this thing, that goes on the outside, and then the polynomial that we're trying to divide goes on the inside. So x cubed plus x squared minus 2x plus 3. Cool. So that has set it up there. Now that I've done that, what I'll do on the screen share is leave up the steps that you follow. So if you want to bounce between the screen share and what you've got on the paper, that should keep us on track for what step we should be going on. So far we've done like step 0, which is set it up. What's the first thing we should now start doing?
Divide the leading term.
Yep, divided leading terms, that's right. So what's that division look like?
X to the power of 3 over x.
That's it, yeah. This is the biggest of the inner, this is the biggest of the outer, or, the more accurate term there would be the leading terms of them, yep. X cubed divided by x, so x squared. Whatever the result is, we'll put it up the top here. And yeah, that's what step 1 says. So if you have a look at the screen share bit, we start by dividing the highest order term of the numerator by the denominator, and then recording the result. Awesome. Next up. Step 1's completed. Step 2 is next.
You multiply x squared by x minus 1 and then subtract from the polynomial.
Yeah, that's right. So step 2 says take this thing and then multiply it all the way through by that. X squared multiplied by x is x cubed. X squared multiplied by minus 1 minus x squared. So that will be what I've written as step 2. You multiply whatever that result is by denominator. And, I've just sort of given those results like names just so it's easier to know what I'm referring to in the notes. And then, yeah, like you said, we're going to perform a subtraction. Again, my preference is to put brackets around it so I don't forget that the negative sign has to apply to all of it. What does this subtraction look like?
2x squared minus 2x plus 3.
2x squared, yeah, okay. So first bit would be like the x cubed, they cancel out. And the 2x squared is going to come from x squared minus x squared. Double negative makes a positive, so x squared plus x squared, 2x squared. And then, yeah, there's zeros down here, so everything else is just going to drop down. Minus 2x and plus 3. That's one iteration done. Still got a fair bit to go, though. So, what's the rest of it going to look like? That's how we get into like step 4, which tells you repeat steps 1 to 3 until there's no more. I didn't really know how else to word that because there's a few stopping conditions. Most of the time, you're going to do it until you run out of x's. Uh, 2x squared divided by x. Yeah, precisely. So by the way, you're direct messaging me, just so everyone else knows I'm not just sort of saying things out loud. 2x squared divided by x, yes. So you take this bit here and divide it by the other bigger bit. 2x squared divided by x. Sorry, 2x. Yeah, fix it. Nice. What else?
multiply 2x with x minus 1 and then subtract.
Yep, that's good. So whatever the result is, we don't grab the whole thing. I see that happen sometimes. We'll grab the whole thing, just whatever the result was in that step. So 2x times x gets you the 2x squared. Again, always checking to make sure, did we get the exact same thing? That's another way to like not make that mistake ever. If you don't get the exact same thing down here, something's gone wrong. But yeah, 2x and then times the negative 1, so negative 2x. And yeah, we then also sped through to the subtraction bit. What does a subtraction now look like?
It will just be 3.
Yeah,
Left
it'll just be 3. That's it. 2x squared minus 2x is 0. Minus 2x minus 2x. Double negative cancels to a positive. So that now reads negative 2x plus 2x, which is also 0. And well, there's a 0 here, so 3 is going to drop down. This is basically finished. So as far as how you now present your answer, that's going to depend on what the question says, which in this case, it just says divide the polynomial by the accompanying linear expression, in which case it's kind of ambiguous what it's actually asking for. What I would expect they're asking you to do is take the quotient, so that's the bit on the top, x squared plus 2x, and then express the remainder afterwards. Can anyone tell me how I express the remainder afterwards? There is a bit of a nuance around how you do it. You don't just write 3. There's something else that comes along.
Plus 3 over x minus 1.
That's it, yeah. So basically, in other words, this is the bit that was perfectly divided, and then this is the bit that has yet to be or couldn't be divided. And yeah, what we've essentially done is convert this cubic into exactly this. So this thing here is identical, is equal to that there. In most cases, we're going to eventually start learning how to pick our denominator such that we do get a 0 at the end, because as it stands, having it like this is probably almost worse to have, because when you go ahead and try to put it into its factors, you're not actually going to end up with the factors in a way that you want to have them anyway. Cool. All right, that's one done live. This is all basically the same thing over and over again. Trying to think of if it's worth doing another one live like that, or if we do still another one, but a little bit. Yeah, actually, we'll do the x squared one. Let's try that. Yeah, why not? Okay, I'll write out the next one. So 8a, we're going to end up doing squared minus 2, then 2x cubed minus 6x squared minus 4x plus 12. So procedure-wise, nothing actually changes, but how it's going to look is going to change a little bit. Who's going to be brave and give it a shot?
You get 2x for the first part
Yeah, so
after the division.
That's right, yeah. So you took the 2x cubed, you divide it by x squared, you're going to get 2x. Perfect. Step 1 knocked out. Nice. What else we got?
And then multiplying the x squared minus 2 times 2x.
That's it. You take that, multiply it through the entire thing. That's going to get you 2x cubed from the 2x times x squared. And then you're going to have 2x minus 2. Now, I've always just kind of put it here because I'm a bit lazy. What you probably could do, it's not wrong to do that, but to make life a bit easier for you guys, you'd probably want to put a little 0 in there and then bring this over so that everything's aligned. Because when you do 2x times -2, you do get -4x, and at least that way now it's vertical as opposed to trying to do it off a diagonal. Granted, this maybe also could look a bit messy because you got random zeros in there. It's a personal preference thing, however you want to do it. But yep, looking good. What else?
And then I think after the subtraction, you'd be left with -6 squared plus 12.
Yeah, looks pretty good to me. So these are going to cancel. The negative is on this, so that's fine. This is just going to be -6x squared, like you said. These are going to cancel because double negative makes this a positive. So another cancelling. And, well, 12 just had a 0 on it. Nice. That's one iteration done. Well done. At least one more to go. Yeah, I think that's just one more to go now.
Yeah, it's just -6 this time.
That's it. Yeah, because you're taking this one, dividing it by this one. -6. Nice.
And then you're subtracting -6 x squared plus 12.
Yeah, because you're multiplying it through and then doing the subtraction. That's right. -6x squared. And -6 times -2 gets you the 12. Oh, look at that. They do cancel out. Easy. You do your subtraction. Yeah. Easy. So if we're going to express it the same way we expressed our previous answer, what do we write as like our final answer here?
Sure.
I think you cut out there a bit, sorry.
Did you just write it out as 2x minus 6 since we don't have a remainder for this
That's
one?
exactly
Or?
right. Yeah. So you would look at whatever this is as your first thing, the quotient, and then you would look at whatever the remainder is and do it divided by whatever you had, but 0 divided by anything is still just 0, so it's not going to go there. And that's your final answer. So basically, this is now converted, so this is a bit more trickier now because you've still got to consider this term. Basically, this thing divided by that is that. In fact, I probably should have said the same thing over here. This thing divided by this is that. Yeah, it's not just this equals that, it's this divided by this equals that. I think I misspoke last time. Cool. I mean, that's both, like, again, we did the same procedure there, but it just looked a little bit different. All that to say, yes, you're just going to repeat that process over and over until you get to the end. Now, this one didn't quite have it. Sometimes you'll get something like, I don't know, let's say an x there, and just hypothetically speaking, there are some circumstances where you could have like 2x plus 1 or something like that on the bottom. The reason why you would stop here is because of this division, right? If you do 2x divided by x squared, you would end up with 2 over x. And as soon as you have like a non-perfect division like that, that's also grounds for terminating it. Cool. So we didn't quite see that today, but I guess we saw it in the example. Yeah, that's basically all of it. So there's no real other things to have a look at, I guess, other than maybe going back to this one. So maybe instead of doing that, I'll give a little bit of a teaser as to where this is headed now. I kind of mentioned that this procedure is there to try and get it into a factorized state. And we can actually have a look at that with the example we just did. So, you know, we had a remainder of 0 when we did this. What that actually ends up meaning is we can say the following. So 2x cubed minus 6x squared minus 4x plus 12 divided by x squared minus 2 is the same as 2x minus 6. All right, that's what we've achieved by doing our polynomial division. We take this factor over here and bring it over to the right hand side. 2x cubed minus 6x squared minus 4x plus 12 is equal to 2x minus 6 x squared minus 2. Now, when it comes to solving polynomials, all we're doing is trying to figure out where does a polynomial equal 0. Trying to figure out where this thing equals 0, difficult. Trying to figure out where this thing equals 0, not as difficult, right? So if we follow this to its natural end, if I now said solve this polynomial, what do we then go and do?
Use null factor. So for the first set of brackets, you could assume that x could equal 3.
Yep.
Since that cancels out. And I think for the second one, you could assume that x is root 2. Square
That's
root of 2.
one of the answers, yeah. Reminder with quadratics, when you do the root bit, you do have a plus minus attached to the root.
Yeah, so plus or minus root of 2.
Yeah, that's it. So you get to this stage here, plus minus root 2. And you know, there might be other restrictions in there. Like for instance, if it was a graph, it might have a domain restriction, like perhaps x can only be positives. I don't know, that's just sort of a hypothetical there. Sometimes it does, sometimes it doesn't. Which that's a lot more common when you hit exams, right? Like exams will be like, cool, you've got your solutions, especially in a tech active, by the way. They'll give you a set of, well, the polynomial will have a set of solutions, but then you're going to have to go back and realize, hang on a minute, like maybe, and quite often, x could be like a length or a width or something, right? So having negative numbers doesn't actually become valid for that scenario. That's when you would now knock off any of the nonsense negative answers from that. Cool. So that's where it's headed. The next thing we end up having a look at will be how do we actually pick this factor, this divisor, at least in this case. Because if I just told you solve that with no other information, like for instance you didn't know what this was, you would now have to figure out either this or perhaps this one, whatever the factors are. How do we go about that? That'll be the next time we visit class 1, so this class again. But I'll just sort of introduce it now so it won't be too fresh the first time you see it. So this is where we look at what's referred to as the remainder theorem, which then gets repurposed as the factor theorem. So let me just pull up my notes on that so we can do a little bit better than what the textbook has. Cool, okay. So back to the screen share, remainder theorem. So we've just gone through a full procedure of doing polynomial division, and sometimes we get a remainder, sometimes we don't. If all you care about is the remainder after a division and nothing else, rather than do a polynomial division, you can just make use of the remainder theorem, which is simply to identify what your a and b are, which I'll point out in a bit, and shove that into f of x, which is your polynomial. Now, f of x is the polynomial. The a and the b are going to come from the linear coefficients. So any generic ax plus b, a is going to be the coefficient of the x, and b is going to be the constant at the end. So if we're dividing by x minus 2, basically put, the a is now going to be 1, and the b is going to be negative 2. So you take your b of negative 2, your a of 1, into your polynomial f of x, and that'll get you a remainder. It's a nice neat trick. you can now find the remainder in just a few lines of working in algebra rather than a whole sequence of polynomial division. How does that help us? Well, a factor simply just means that the remainder after division was 0. So basically, what you end up doing is you test a sequence of options until you get a remainder of 0. Then, once you've tested your options, you sort of reverse engineer that back to figure out, okay, well, I subbed in this and I got 0, therefore, I can now figure out what my A and B are, which gets me to my linear, the thing that I was dividing by. That gets us the factor that we now know we can divide by. So what does that actually look like? What you end up doing is when you're testing options, because, if I just say test options, you could test God knows what. What you end up doing is you look at whatever the last term is, the constant of the polynomial, and basically just start by listing out all the factors of that constant. So the constant is 6, you're going to have plus minus 1 and plus minus 6, and then you're going to have the 2 and the 3, both the plus minus versions of those. These are the list of numbers you're going to test in the function. Start with the easiest, work your way out to the hardest, partly because, well, it is easier to do it that way, but also because the way, you've got to remember that examiners actually write these questions. If they're choosing plus minus 6 as one of their answers, they really hate you. And so in the interest of saving time, they'll pick any of the smaller ones. That's just sort of by convention. They'll do that to save time, make it not as painful. They're not testing how fast you can speed through algebra. They're testing that you know the procedure and can do it proficiently. So what does that look like? Well, plus minus 1 is going to be the easiest, so start by testing off 1. And what that means is you shove that into the f of x as the x term. In this case, we got a 0 immediately. Again, they try to write them to be easier. If you didn't get a 0, if, for instance, you tested -1 first, in this case, you would have gotten 8. You basically just keep going down your list until you hit 0. Now, here's where you take it from here. That number that you tested is going to be equivalent to -b over a, right? We have this statement of f of 1 equals 0. We just proved that over here. But we also have the generic factor theorem, which is as long as f of -b over a is equal to 0, we have a factor. So we can sort of see the similarities between these things. The only difference is this one says -b over a, and this one says 1. From that, we can determine that 1 is equal to -b over a. Now, we don't have too much time to explain why this is simplified as such, but just sort of take it for granted for now. We're going to assume in all these cases that a is equal to 1, and that allows us to then say that b must therefore be equal to -1 in this, simply by plugging in the a equals 1. We'll explain more about why a is 1 in this circumstance in the time we actually look at it formally. So we have our solution for a, we have our solution for b, therefore our linear is a, 1, and then b, -1. So the linear that is a factor must have been x minus 1. And to prove it, you could chuck that through the whole polynomial division. If you get a 0, you're happy. You have the factor here, you have the factor here, expand it out to the other side, and then null factor all. Lots and lots of work to be done, which is why these are sort of few and far between in SACs. You might get one of these, and they'll try to make it as easy as possible because, look how much writing went into it. It's a lot. You test your numbers, you list out your factors, you do a full polynomial division, expand it out, null factor law. That's a lot of effort and a lot of marks. So they use them sparingly in real SACs. That's a sneak peek for next time. And that brings us to end of the lesson on that one. If there's anything further you would like me to clarify, I'll be happy to stick around for a couple minutes, or even if you just have a few questions. Whatever you like. I'll leave you to it. Take care, everyone. You too, mate. Take care. Thank you.